Hi there. How are you?
I'm good, how are you?
Not too great.
No?
You want to see a nasty video?
No.
No, it's not that bad. It was worse for me.
Do I want to see this?
Probably not, but look, this was in my room.
Oh, that's not good.
Yeah.
That's not good.
No. I came back yesterday from my parents' place and then I heard something and I was like, oh no, I'm out.
Wow, okay.
Yeah.
So what now?
So I contacted my landlord, but he's in Germany. So then I contacted the handyman. He has like a full-time job and he just kind of does like our stuff on the side.
Yeah.
So he's like, yeah, I'll like call up someone for you, but he hasn't come back to me yet.
So where is it now?
Huh? Where is it? It's just in my room
Just
somewhere.
hanging around. Okay.
Yeah, it's disgusting. And just the thought of it like crawling on my bed and stuff. Ooh.
No, that's, oh god, no. Okay.
Yeah. That was not the warm welcome I wanted yesterday, but you know. The worst part is, it probably isn't even my fault because like, I cleaned up everything before leaving, so I didn't have any food lying around or something. But other people put like trash bags outside and stuff. But because I'm on the ground floor, I'm the one who ends up with it. It's so annoying.
Oh, sorry.
That's okay. It's part of the student experience, I guess. So I got off my mom at like 12 a.m. yesterday. I was like, what do I do? It's crawling around. But luckily I got to stay at a friend's place, so
Okay, good.
that's good.
Hi. Still only got a tutorial submission grade for the first one. I know, I haven't graded all of them. Okay, yeah, I was just wondering because I had some other people. I'm just behind.
Alright, let's make a start. Alright, so 2/3 of the way through. Just so that I can get a general sense. We wrote a midterm last week. It was totally fine. It was so. Oh my god. Just general.
Tom was out quick. It was not very difficult.
Okay, hello people over there. Can you give me an indication on the midterm? Up. Alright. Kind of, okay. Alright. Also, people in my tutorial, I'm really sorry I haven't marked your stuff yet for the tutorials. I'm behind. I'm going to do a big grading day tomorrow. Promise. Also, I could rush through stuff today and next week, but this seems counterproductive. So my suggestion is that we actually have, on Thursday, instead of having just tutorials, we'll have an hour lecture and then following that an hour of joint tutorial, so that I can actually talk through the stuff without like sounding like someone doing it really fast. Okay. So I will let you know the details of where the lecture will be. So basically on Thursday we will have a lecture from 2 until 3 and then a tutorial from 3 until 4 and then you'll be released into the wild. Yes?
A question on the weekly quizzes and
Yes.
the grade assignment. There weren't any for last week,
Right.
So was there homework assignment and there wasn't a quiz?
There was a midterm. I felt that was sufficient.
Okay. Just that I'm not missing.
Yeah, nope, you're not missing. Okay, so I will put up an online quiz for this week. There will be a homework assignment due this week, and the same next week, and then we'll be done. Yes.
Will the lecture on Thursday also be recorded?
Yes. Yeah. I mean, technology willing. I will do my best. I feel like last year and this year has taught me to never say with certainty, yes, this thing will happen. I'll be like, yes, I will try and make this thing happen. It might not. Alright, so what have we got on the cards for today? So we're going to finish up talking about integrals. We've got some more stuff to do on double integrals. And then we're going to talk a little bit about triple integrals. basically once you've done double integrals, you kind of know the techniques that we're going to use for triple integrals. It's just now you do 3 instead of 2. Then we move on to a new section, vector and scalar fields, which basically take us into the home stretch and will lead up to the final chapter that we're looking at next week. So we'll finish chapter 15 this week, which kind of gives us the last bit of theory that we need, because basically everything we've done up until now has been building up the tools that we need in order to understand Maxwell's equations. If you think back to the first lecture, I showed you those 4 equations. We're almost there, not quite. Okay, so today we start with the final stretch. All right, so double integrals. So just a reminder, we said, okay, if you're doing a double integral, the idea is that you have some boundary, some little space on, say, the xy plane, and you're trying to integrate some surface over there, so you're looking for volumes. Okay, so if you're integrating, if you imagine thinking in a triple integral, then it's not clear what exactly you're integrating to, because you're taking a volume and you're integrating over that volume. Okay, but yeah, we'll get there. So we express a double integral by these 2 things, and it says over some little domain here, we are integrating this thing. But what we said last week was that often we can split our double integrals into 2 integrals of the kind that we know. So we talked about y simple and x simple domains, which you don't end up really thinking about very much. You just think about how can I integrate this thing, as you'll see in a moment. And you split up, so you end up doing an integral, for example, with respect to x, which you might have some y's sitting in your limits, and then you end up with a new thing that you then integrate with respect to y. Okay. Let us have a look at an example. So, we are integrating this thing, e to the y cubed, and we're integrating it firstly, so the way it's written here is we're integrating from root x to 1 with respect to dy, and then whatever we get out of there, we're going to integrate from 0 to 1 with respect to x. But if you have a look at this, I mean, the first problem is, what is the integral of e to the y cubed with respect to y? I don't know. Okay, so that's a problem. And if you were just given this integral here, you would kind of be forced to say, sorry, I can't do that. But this is a double integral, so maybe if we switch the order of integration, then we can do something. So, but how do we do that? Well, let's have a look. What is the, okay, so what is the integral? What do you have to differentiate in order to get e to the y cubed?
E to the y to the 3, and then in front you have 1 over 3y squared. That doesn't work.
No, try, no.
Can you not use like substitution?
So,
Like
so you
y
can,
to the
so a homework
u.
thing is to convince yourself you can't integrate this bunny. I mean, it looks suspiciously simple, like you totally should be able to. In fact, there's one that you should have seen a lot before that is really annoying, which we will see later. We know we can actually integrate. The good old Gaussian should be able to. It's so simple, it's so innocent. But no. But actually, yes, later today we will integrate this. But using single integrals, the way we've done. Okay. All right. All right, so what does it mean if we want to change our order of integration? So here, this is saying first integrate with respect to y, then integrate with respect to x. We want to swap this around, so we want to change how we're integrating. So let's look at the domain that we've got and see if we can rewrite it. So at the moment, what does this say? So let's just look at our domain. It says at the moment we're going from 0 to 1 in the x direction, so we've got, those are our x bounds, from 0 to 1. And then it says in the y direction we go from root x to 1. So we're going from root x, which looks like this, to this line here. So the region that we're integrating over is something like that. And now you start to see why we drill you in drawing graphs. So let me just make some notes here. So this is the line y is equal to 1. This is the line y is equal to root x. This is x is equal to 0, and this is x is equal to 1. So what we'd like to do, to see if maybe we can do this in some easier way, is we'd like to instead integrate from something to something with respect to y, and from something to something with respect to x. So the only thing that I've changed is the order of integration. So now I need to think about if instead of having the kind of the variable limits in the y integral, I want them in the x integral, what should they be? So I'm now thinking about what do I integrate x from if I'm going from this purple line, but now I want to integrate x to this line here. What is that line in terms of y rather than x? It's y squared. So I could rewrite this as x is equal to y squared, and then I can change my limits, and I can say, well, I want to integrate x from this line here, which is x is equal to 0, to this line here, which is the y squared line. Yeah?
So does that mean that for the first integral, the numbers on the first integral will never change? That it'll always be, for, in this case, from 0 to 1 on the first one?
So we're about to look at that and check. In this, it will change.
Okay.
So now we have a look and say, okay, now what am I integrating y with respect to? Well, I'm integrating y from this line here to this line here. So in this case, it's from 0 to 1. But it could have been something else. It just happens that they coincide. So you might say, well, what have you done? How has this made this any better? But this has made things a lot better because we don't have to worry about this bunny right now because we're integrating with respect to x. X doesn't care about y's. Okay, and you might be like, well, now you've just prolonged the problem because that's going to come over here. But what happens when we integrate from 0 to y squared? So let's just write this out. What we've got is the integral from 0 to 1, e to the y cubed dy, integral from 0 to y squared dx. What is the integral from 0 to y squared of 1 dx?
Y squared e to the y to the 3.
Okay, I'm wanting to, so I've got a 1 here. I'm integrating 1 with respect to x. What does that integrate to?
X.
X. And then if I put my limits in,
Y squared.
I'm just going to get y squared.
And now you switched everything again from the first line. Why did you get rid of the e to the power of y to the 3?
Because this integral is with respect to x. And so this just acts like a constant because it only has y's in it, which don't get integrated. So it pops out and sits there like a constant. It's fine. This is weird. Okay. So end up only integrating 1 with respect to x from 0 to y squared, which I get is just y squared minus 0, which is y squared. But now look at this delightful thing. Now we can totally integrate this bunny. We totally can. Okay, you just, yes? Okay, so life just got better. What is the integral of e to the y cubed times y squared?
Well, e to the y cubed.
It's just e to the y cubed. So you could, if you're not doing this in your head, that's totally fine. I couldn't do it in my head. You would probably do this with substitution. You put like z is equal, or w is equal to y cubed, e to the, and then you'd have e to the w, and this, so there's actually a factor of, I think, half or a third coming in somewhere. I think a third. Okay, I'm not running through the integration. This one is straightforward. I think. Yep. Yes. Yes.
Could you explain one more time how you went from square root of x to 1 to 0 and y squared? How you initially changed the boundaries of the integral?
So when you're integrating over a surface, you can choose whether you integrate first with respect to x or first with respect to y. So I looked at that. So are you happy with how I got the region we were integrating over? So looking at that region, it is both y simple and x simple. So we could integrate either way. So I decided to change from the top form to instead integrating first with respect to x. So what I looked at was I said, okay, I need this line is my lower limit for x, and this line is my upper limit for x. Because if I'm integrating first with respect to x, I'm always integrating along these bits. So I need to integrate from 0 to whatever point I'm on here. And I need this line expressed in terms of y, not x. So I just said, well, y equals x, y equals root x is the same if I square both sides as x is equal to y squared. So this line here is the line of y squared. So I'm going to suggest we carry on. You can ask questions in the touch. Yeah. The moral of the story is, although double integrals might seem trickier sometimes they're actually useful because you can shift things around and integrate stuff that you might not be able to integrate if you just had one integral to deal with.
If I didn't have the sketch,
yeah,
how would I know how to switch them around? Like, how would I know?
I don't know.
Oh, really?
So that's, I mean, I can't do it without a sketch. So that's why I will always draw the sketch. If worst comes to worst, I will get GeoGebra to draw the sketch. Yeah. Yeah.
In this case, like, the sketch makes it very clear to see, but don't you just take the boundaries of both integrals, and then you've got the boundaries in blue, with y as the isolated variable, and then you just square both sides and you get x as the isolated variable. So can you always just solve for x in your equation in terms of y, and then use that as your new boundary?
But then why would you know that you don't go from y squared to 1? Basically just substitute square root x to your value that you isolated. But how do you know that instead you do from 0 to y squared, for example, that you have to switch them? Do you get what I'm saying?
Yeah.
So as far as I know, there isn't just a routinized process, because, I mean, this is quite a simple boundary that we've got. But you could imagine that we had something which, instead of having like straight lines here, here, and here, had other functions. And then you're really going to want to spend some time thinking about what it looks like and actually switching the variables manually. So there might be a routinized process, but I don't know it. And I would worry about using it, because for me it's really important for me to know what this looks like and how I'm changing it. All right.
But then, sorry.
Yeah.
To go back on what you said, you're saying that if we have multiple functions, how can we have to calculate from those functions the functions that limit y if we want to change them in a specific case?
Yeah.
Okay. But then if we only have the functions delimiting it, how can we calculate the other functions that are delimiting it, like putting the limits on the other side?
Well, I mean, you'd be given them.
Yeah, but you said you were given only the ones limiting the x. In that case, if it might...
No, we were given the ones limiting x and y.
Oh. Yeah, I guess.
We've got x equals 0, x equals 1, y equals root x, and y equals 1. So we had 4 limiting functions. It's just that 3 of the 4 limiting functions are really simple straight lines. But you can imagine a situation where they were not. and then you need to do some thinking.
Yeah, but in the case where there are not, but so you're saying there won't be a case where we're going to have to calculate like what functions delimits the other axis.
Right.
Okay.
All right, so take a moment and just think about this. See what you can sketch, see what you can figure out for yourself. As a starting point, I would recommend trying to just draw the footprint on the XY plane that you're integrating over. So the things that you need to think about is, what does this parabolic cylinder look like? What does the boundary, like what is your domain that you're integrating over? And then, okay, what is the surface that you're integrating, really? Sorry, I'm just swapping over to a different. Of course. Where is my mouse? Move that also. Okay, that's not working. What is normal?
Why am I not normal? Why are you the one to decide what is normal?
All right. So things to think about. Firstly, parabolic cylinder. Did you figure out what that looked like? So if you look in the XY plane, it's going to be tricky. you can see, so now I'm looking straight down. This is positive x, this is positive y, and that's the cylinder that we're looking at. Okay, so that's kind of demarcating part of our space. We want the line y is equal to 0, so that's this line here. That was one of our, this line here. So that's one of our boundaries. And we also had z is equal to 0. So that's actually the xy plane. So if we think about what we're looking at here, we're looking at the chunk where if we cut along the z-axis and along here, we're looking at this bit there. But there's one more thing that we haven't added in. We're thinking we've also got a plane that's now cutting this. Let me add in our plane. So now,
Wait, what's the plane? Oh, z is equal to.
yeah, so you can start to see this shape that we're getting. It's like we've taken our, so we had our parabolic cylinder doing its thing, and now we're kind of chopping it weirdly like that.
And how do we know if we need to go to the x positive direction or x negative direction from the slice? Because you could have both sides within the planes, right? The way we cut it.
So what we'd look at is, if you look like so, you'll see, so this is our positive x, that's negative x. So we're looking at our, we've got all of x, we're going from minus, so I just made a is equal to 5 here. So you can see from here we're going x is minus 5 to 5 in this direction, and our y is going from z is equal to 0, so this bit here to this line here, and then we're going to integrate up to the plane that's chopping things.
Which side of the parabolic cylinder are we getting within those planes? Because when we bind the planes z equals 0 and y equals 0 and that place there, when it slices, don't we have a left side and a right side within those boundaries we said before?
Okay, but it says, so it's bounded, so you want to find the solid within. So, okay, so I agree, you say z is equal to 0 is this line here. It could be either side. You say y is equal to 0 is this, is this. Y is equal to 0 is this. So we know that we're here. So once we've added those, we know that we're on the top half, and we're either here or here. And then you add this parabolic cylinder, and you say, okay, well, we must be in here, because that's enclosing a space.
On the upper part of the slice, the diagonal.
Yes, well, the upper part is because of the z equals 0. This side is, I mean, the upper part is because where the y, z equals 0 is the xy plane. And as soon as we come up here with the cylinder, it has to be up here. Well, the final bit that we'll get will be where the plane goes.
Along the plane.
So this blue plane, the additional plane, gives us a lid. So once you get the lid, you know, so if this plane had been underneath, then we would have taken this bit. But because the plane is up here, we take the top, the bit that's above the xy plane. So so there's a lot of thinking that goes into this. Okay, let me just switch back over. Okay. So, I mean, when I tackle a problem like this, there is a lot of sketching. Okay. These are my notes. Like, there's sketching and there's scratching out. We're not expecting you to just like, I mean, some people can just draw things, but probably you'll do some scratching out, that's fine. But what I do end up doing is trying to draw things that are helpful. So for example, I will try and draw the boundary, the domain. So I'm drawing x versus y. So I'm imagining I'm looking down on my solid. What is it that I see? Well, the first thing that I know is that I need to have just make sure I get this right. Let's have a look at this over here. What does that look like? What is y is equal to a minus x squared over a? What nature of thingy is it? If I'm just thinking in x and y. Okay, tell me more. Is it a happy or sad parabola?
Sad.
It's a sad parabola. Okay, if a is positive, how is it shifted?
It is shifted upwards.
Okay, and what are its roots?
Minus a.
Right, okay. So we can immediately say, alright, this thing will look something like this. Got an A, I've got a minus A, got an A. Okay, I also, looking like this, I know that my x-axis is coming out here. My z-axis is coming out here. So the plane y equals 0 is this plane here, coming out like so. So I must have really that this is the boundary region that I'm looking for. This is the domain that I'm looking for. So I'm integrating over that. And I'm integrating over that up towards wherever my plane, this other plane is, whatever crazy thing it's doing. So now I can put together the double integral. So let's just formalize that. My x limits, well, looking at this, I'm going to go from minus a to a. What are my y limits? Well, I'm going to go from y is equal to 0 up to wherever I am on that parabola. So my y limits will be from 0 to a minus x squared over a. And
just say A. Does it say the y-intercept?
no, because remember, because it's not always A. Sometimes it will be A. It will be wherever you are over here. So for whatever x value, you're going to be integrating. Yep. So then what we end up with is something like this. I think it should be a minus.
Couldn't I make the same argument for the x boundaries though? It's not always minus a, it's not always a, but it's also in between a lot of times.
So you could, but then you'd be changing around. So the way we're doing it is we're saying if we're taking x from minus a to a, then we're letting y be the one that varies.
Okay, I see.
You could switch it around. Yeah.
The boundary z equals 0, we don't take it, sorry, the boundary y equals 0, we don't take into account in the two-dimensional
Right.
variable. Because I would cut it.
Well, we do in the sense that y equals 0 means we're not adding in this bit over here. It's stopped us here. Okay, where do you go from here? So there are so you could integrate this straight off. But there's one thing that you might notice. So notice we'll be integrating with respect to dy. So if we do a little bit of rewriting, what are the things that we can ignore? So firstly, this is a sum of things. So this whole thing is really three different integrals. It's the integral with respect to a, it's the integral with respect to integral of minus x, and the integral of y. So I'm going to just shorthand this to minus the integral just the same way that if you had a bunch of things in a single integral that were added together, you'd split it up into the sum of the integrals. One of the things that you can notice here, x, when it gets integrated, is going to integrate from minus a to a. So it's going to exactly cancel. So if you're feeling kind of smart, you could say, well, this integral is going to have to be 0, because this is an odd function. But you don't have to. So I'm going to stop here. You should finish this up. You have, so transfer these limits here appropriately. I was just doing shorthand. And you will find that this one goes to 0. And the rest follow. Yeah.
How do I know where to put dx, dy, dz, dx, dy? Like, where does the dz person come from?
That isn't a z. That's a crossed out.
Oops, okay.
So this is just shorthand. What I would recommend that you do is you write out 3 integrals, each of which basically looks like this. It's just the first one has only the a, the second one only has the x, the third one only has the y, and you integrate each of those for practice in this appropriate order, and you will find that this one goes to 0.
Would the y dy also have a dx in there, or?
Yes. Okay, so there's going to be lots of integration practice in the TUT this afternoon. All right. So what's an improper integral?
So are we just, if we're just finishing that, or like how do we incorporate the z and the weird plane thing? Because that's like the hardest part for me.
So we incorporated so we're integrating up to the plane. The plane is the surface we're integrating to. So there's our plane.
What's already there?
It's there. We're done. You just need to finish these integrals. I will put the solution in. So basically, if you look at what they gave us, this and this and this were our boundaries. They went in to give us our boundaries, and this is the thing that we were integrating. That's the surface that we're trying to find the volume under, subject to the boundaries.
How would I know that I integrate underneath, so from 0 to that?
Because you look at the volume that gets created. So that's what we were doing.
How, like, if I don't use GeoGebra, how would I visualize this plane? Or how would I draw it?
So, I mean, the first thing that you do is you draw this bit.
Yeah, that I get, yeah.
Okay, and then you'd say, okay, well, it's a plane. What is it doing? So, let me show you my diagram here. So I drew one cross-section of the plane like this, and I might draw some more level curves so that I got a feel for where the plane was going.
So I just calculate, I put in minus and this.
Yeah. Okay, so what is an improper integral? Cast your minds back to calculus 1. Yes.
Sorry. Isn't it when there's a limit to the integration that is not a real number?
Yes. So you will have seen things in your past that look like, I don't know, okay, things that have limits that are not real numbers, usually infinity. You might also have seen things like this, where at one of the limits, your integrand isn't defined. Ring a bell? Obviously, we have to deal with these in double integrals, and the good news is we treat them pretty much the same way that we treated them in calculus originally. So you use limits. Yay, limits! Okay, not going to spend a lot of time working on this, but to see where they might crop up, if you're in 2d. Let's have a look. So we've got e to the minus x squared dA over the region x is bigger than 0 and this thing here. So if you sketch that region, okay, so x is bigger than 0 says we're on this side of the y-axis. And what is this? Well, if we draw the line, this is the line y is equal to x, this is the line y is equal to minus x, and this says that y has to lie between those two lines. So basically we're integrating over this whole region that just is unbounded. So you can see straight off we end up with an improper integral, because really if we wrote out this integral, we get, we are going from, so I'm going to do it with respect to y first. So we're always integrating y from minus x to x, so that's fine. But the problem comes, what are we integrating x with respect to, we're going from 0 up to infinity. And we have an improper integral. Can we do anything about this? Do we want to do anything about this? Yes. I will show you, because it will hopefully remind you, and you'll see that you're just using what you knew from calculus previously. Whoops, what happened to my y? Okay, so the first, our problem is only coming in at the second part of the integral. We can do the first. Let me do the first bit. Oh, yes, we can totally do the first bit. So you might look at this and go, but Claire, you keep telling us we can't integrate e to the x squared. And I'm totally telling the truth, but we don't have to, because we're integrating with respect to y. Okay, so we have integral from 0 to infinity of e to the minus x squared dx, and we're just integrating from minus x to x dy. So we're integrating a 1. So that just gives us so that just, if we integrate 1, then we get a y, which we integrate from x to minus x. So that gives us a 2x. Alright, so we end up with this. Okay, I'm moving fast through the integration. You need to just go and recap if it's feeling hazy. How do we handle these? So from calculus, sorry, Tom, we say, well, okay, we're going to, what we do is we replace this with something, and we're going to take the limit as that something goes to infinity. So we've got, let's best write this, 2, the limit, let's use an r. Does this look familiar? Okay, and you can just trundle through this. If you finish that up, you'll find that this is actually equal to 1. So the net, what do we get out of this, is this one happens to converge. It's an improper integral that we can find. But in the same way as you had in calculus 1, sometimes improper integrals diverge. You can't solve them. You just have to do the maths and figure it out. Okay.
Of the second line you wrote, you did the same trick you did in the beginning, where you switched the dy dx's and what you're integrating first and what you're integrating second?
No. I kept the order the same. All I said was I'm integrating first with respect to y. Y doesn't give a damn about x's. they act like constants, so I can just pull this out the same way that I pulled out this constant here when I was integrating.
Okay, so you didn't do a trick. You
I
just
didn't do a trick.
rearranged it because there's no y's in the
Yeah.
equation.
Yeah, so I treated, so even though this looks like a complicated thing, as far as y is concerned, it's a constant. It doesn't care.
And in the beginning, you did the trick so that you could do this again.
Yes. Yeah. Phew. Okay. So I will write up the solution for this, but this is just another kind of improper integral for you to kind of practice. I'm not going to be focusing on improper integrals. I just want you to have seen that obviously they crop up like they cropped up in Calculus 1. And I'm also not going to talk about the mean value theorem. You're welcome to read through this for interest. If you were keen on the mean value theorem in calculus of one variable, you'll be happy to know that there's actually more than one. This is just one of the ones, one of the most useful ones, a mean value theorem for double integrals. Okay. Okay. Who's worked in polar coordinates before? Just can I... Okay, good. Then this is going to be useful for people. Alright, so if I handed you this integral over here, you might justifiably go, Claire, really just don't. Okay, it just please no. Okay, this is just no. Really, no. But it turns out that sometimes it's more useful to use other coordinate systems than the good old x, y that we've been used to. One of the useful ones is polar coordinates. All right. So what is it that we're doing? Basically, we just happen to use Cartesian coordinates with x and y because it sort of works for how we function as humans. So we tend to give an x and a y coordinate, and that means that along our x-axis we've divided this up into equal units, and on the y we've done the same thing, and blah blah blah. But there's no reason that we have to give those coordinates like that. We could, for example, instead say, okay, in order to get to that point, what you need to do is you need to start off somewhere on the x-axis. So you need to start off at the origin with kind of an idea of direction towards here, move through an angle theta, and then travel a distance of r, and that would still get you to the same point. So the trick with using new coordinate systems is basically how do you translate the crazy stuff that you have in x and y into r's and thetas, and the answer is given over here, okay, which is trig and shouldn't be too crazy. So if you have an x coordinate and you want to know, oh, what is it in r and theta, or rather, if you've got an r and a theta, you can find your x's, but similarly, if you've got your x's and your y's, you can translate them into r's and thetas using those.
Haven't we been doing that already, kind of, with parametrization stuff?
Yes.
It looks very similar.
It looks very similar, which is good. So yeah, if you can think of it, I guess, as a reparameterization. But there's a little bit more fundamental thing going on here. You are changing how you think about the space in which you work. Yeah. Okay, how does this help? Let me just make sure that well, what is kind of cool about this, so now let's think about back to this thing that we were looking at, this crazy thing over there. What happens if instead of having x's and y's, we translate all our x's and y's into r's and thetas? What do we get? Well, if we try 1 minus x squared minus y squared, going back here, okay, r squared is equal to x squared plus y squared. So firstly, our integrand becomes quite a lot easier. It's just a 1 minus r squared. But we also need to change how we talk about our area. What happens to our volume integral? Well, if you've got a dx dy like this, you can think about it instead as changing into a little volume like this, a little area like this.
No, the areas don't look the same.
So
at the moment they're not the same. But they don't look the same because these are not infinitesimally small. But basically what we imagine is we shrink it down to dr and d theta are super tiny, and then it's going to be the same super tiny thing. But they have they look fundamentally different. I mean, this is quite a different shape. But you can imagine that instead of cutting up your domain into squares, you could chop it up like this. You'd still chop it up and integrate the same way, summing from, say, r is equal to 0 to r, and from theta equals whatever to whatever. You would still cover the same area with your little bits.
Like if you're like, so now you're talking about the xy plane, then if your z plane is like wobbly, for example, then it wouldn't be the same volume. Because like I can imagine how it would be the same if you had like a straight xy plane. But if it's not, it doesn't, like the position of the area also impacts the volume.
So I mean, the way we're thinking about integration at the moment, we're thinking about like some area on the xy plane, and then we've got some z thing doing its crazy thing here. It doesn't matter how you describe this area, whether you use x's and y's or r's and thetas, it's just going to be the same. And you will translate whatever so this might be initially given to you in x's and y's, but you can translate that into r's and thetas too, and it's still going to describe the same surface. So it's really just kind of a change of variables, in a way. It's not...
Like the domain area that you're describing on the xy plane doesn't keep the same shape if you go from...
Well, you work it out so that it does. Let me show you an example. Okay, maybe I should go back to this example here. All right, so let's look at what we've got in our x and y format over here. What is our domain that we're thinking about there? So I'm just going to pull this. Okay, so if I've got an x and a y, what is the domain that I'm integrating? So x is going from -1 to 1. And what is y going from? What is that thing? It's a circle. Okay, what's the radius of the circle?
1.
Okay, so here's my circle. All right. Am I integrating over the whole thing?
How did I know that this is a circle?
Because think about these limits as saying y is equal to 1 minus x squared. And maybe it would make it easier if you square it. Yeah. Okay. So now, if I think about how I want to integrate this thing, if I'm changing from x and y to r and theta, I want to get this same area here. Well, if I think about the radii that I'm going to need to look at, I'm going to need to look at the radii all the way from the shortest radius out to 1. So my radius is going to have to go from 0 to 1. So here are my limits. My radius
is going to go from 0 to 1. And I also want to sweep out the entire circle with my theta. So my theta is going to have to go from an angle of 0 all the way around to an angle of 2 pi. Okay? So, oops. All right. So now let's change everything in our integral. So I've got my volume. What am I going to integrate? I'm going to integrate, well, let's just put it in some order. So my radius is going from 0 to 1. So I'm just thinking of this as my radius, this is my theta. I'm just keeping a note. This is going from 0 to 2 pi. The thing that I'm integrating is this thing here, and we've said that we can change that to 1 minus r squared. And then the final thing that we need to do is we need to convert this dA, which was dx dy, into spherical, into spherical coordinates, yes, polar coordinates. And the way that we do this is using this transformation here. And suddenly that looks a lot more friendly. What have we got? Well, we've got the integral from 0 to 2 pi, integral from 0 to 1. I've got two integrals here. I've got one that says r dr d theta, and I've got minus so that's r dr d theta. And these are pretty straightforward. So what's the integral of r?
You always multiply by r inside the integral? I thought it was outside from the expression that was written earlier.
So this...
Here. I thought the r meant that you had multiplied by r outside the integral.
So you replace the dA, or the dx dy, by r dr d theta. Because that is the area of that little thing there. And this r is a variable, so it has to be inside the integral. Yeah.
This is in 2 dimensions, right? We're not talking 3 dimensions yet.
Kind of. Yes. Well, we're getting a volume.
Are we getting a volume? Because it's the r d theta instead of just the r, or just the theta.
We're getting a volume because it's dx dy, which we happen to convert to dr d theta. But we are integrating this. What is this?
Well, until we also get a change in the z-axis, then it's just an area, right? Like in color coordinates, you would just have whatever shape you've got coming out on the z-axis, right?
Yes. But it's still a volume.
Is it the same as calling it cylindrical coordinates? Or
No.
something else again?
These are polar coordinates, which is circular coordinates.
Yeah, but like because you just said like it's coming out and then it would be a cylinder, it's a circle, but it's not a circle. I don't know, whatever.
Let's just finish up this, and I think you'll see what this is. Okay. So what is the integral of r with respect to r? What is the integral of x with respect to x? Okay, so that's r squared from 0 to 1. I feel like everyone is kind of zoned out, which is fine, but I'm not going to drag you kicking and screaming through integrals in this state. I will finish up these integrals. You should finish up these integrals. Do lots of integrals in the tutorial, but I think this is not a great use of our time right now.
Can I ask a really simple question?
Yeah.
Do we work inwards, outwards for the dRd theta?
Exactly like you do for x and y.
Which is inwards, outwards. We have
Yes.
two integrations out here.
Exactly the same as you do for x and y. Whoever's on the inside, you do first. Alright, I was going to do this kind of cool thing over here, which shows you how to integrate the thing we don't know how to integrate. But I will put it in as an Easter egg in the notes. It's kind of beautiful, but I think you're not feeling it right now. So not ready yet. Okay. So I'm going to actually stop with the integration here. You can practice this. This is, I mean, remember when you first started integration in one variable and it was just a grind and a slog? Sorry. It's more of the same. You just kind of need to swap in how you do this. And we can't do it in only an hour. For interest's sake, and because if you go on to do any kind of general relativity, anything that involves kind of curved space-time, you're going to want to start thinking about these things. This idea of changing from Cartesian coordinates to polar coordinates is just one example of a change of coordinate system that gives you a way of changing from flat Euclidean space to curved space-time. So you can read about change of variables in double integrals. You don't have to just use polar coordinates. You could change into whatever crazy coordinate system you feel like using. So you can read about this here. Basically what this boils down to is you might want to go from Cartesian, nice chopped up squares, into some weird ass thing like this. How do you do that? Well, there is a routinized way to do that. You will take your original integral that looks like so. You will work out what your equivalent little area volume, your area thingy is. So we found it was r dRd theta for polar, but in general it's found like this, and you'd convert your function that you're integrating into another function with respect to the new coordinate system. So this is the general transformation from one set of coordinates to a different set of coordinates, and you can play around with that. I'm planning to run a little mini course on differential geometry where we talk more about this. So I will put this example in. So I will mark on these notes what is for interest, what is required for the course. Okay. Triple integrals you'll see in the tutorial. They are basically rinse, repeat 3 times what you've been doing 2 times. There's nothing particularly sophisticated here. I think the only thing that's more difficult with triple integrals is, I mean, it was bad enough with double integrals having to draw the region we were integrating over. Now you're integrating over a volume, so you're trying to visualize what that volume looks like. It's harder. You need to practice. Yes?
Does that also mean that we can integrate to the n number of integrals?
So, yeah. The sky is the limit. And in fact, sometimes you will.
And so here what we're trying to find, like, what is it called? Because before we were trying to find a volume,
right?
And now a hypervolume.
Kind of a hypervolume. I think we stopped trying to call it things.
Yeah.
And we just kind of.
We just know we can do it.
Yeah, we know we can do it. We know when we want to do it.
Yeah.
We do it, but we don't talk about it.
What would the units be? With area, you could have like meters squared, you could have meters cubed, you just get
Meters to the full. What? Yeah. I mean, the thing that you're thinking about is something like, suppose, I don't know, you've got the temperature measured at every point in a room. and you're interested in, or maybe, and you want to calculate something, maybe you have a way of calculating the energy in the room based on the temperature over it, or the energy in a volume or something like that. That's the kind of thing that you're looking at. So you can imagine that it is going to come up. We'll in fact see examples where they come up.
So it's with 4 different things that affect your outcome. You need to compute for all 4.
Yeah. And all the tricks that you've learned, changing orders, changing variables, they all apply, and you do them all. But the good news is, okay, when I was a young whippersnapper, sitting where you're sitting right now, we did not have computers and things like Wolfram Alpha. Okay, so we spent a lot of time actually calculating these wretched things because that's what we had to do. But out in the real world now, you would use Wolfram Alpha or something else, and you just kind of reality check it. But you do still need to understand the process because obviously computers screw up all the time. All right, triple integrals. So before we head on to vector fields, let us just take a moment. If you feel like it, you can stand up and stretch. I'm not going to give a break because we are time stretched. But just like. All right. And now, if you feel comfortable, just close your eyes. Otherwise, look somewhere peaceful. And just listen to the sounds around. Gradually bring your attention closer and closer to yourself and start noticing the breath. Notice all the way that your body changes as you breathe. Feel the air as it enters your nostrils. Feel how your chest and your belly expand. Notice the still, quiet moment between breathing in and breathing out. And as you breathe out, notice how your shoulders relax, chest relaxes, belly relaxes. For 3 whole breaths, just breathe. That's all you have to do. Just breathe. Few more breaths, just breathe. And start listening to the sounds around. Wiggle your toes, give another stretch, give a yawn, and open your eyes. Alright. So I am aware that this course is intense, that there's a lot we've covered. Honestly, if I could have it in 2 6-week courses, I totally would. But it is what it is. I have cut a lot of material out. We are doing the bare minimum so that we can actually get to where we need to get to. I know it is putting pressure on your brains, but at the same time, you know, you have great brains and we're making them stronger. Please push through. You have 2 more weeks. And basically everything that we've been doing each week is required so that we can get to the kind of the punchline next week. This is a very long, drawn-out joke that we are putting together here. Okay, it's
I'm not sure we'll be laughing a lot at all.
It's fun.
I'm not sure we'll be laughing a lot at the end.
you might not be laughing, but I hope that you will look at it and go, oh wow, okay. It's one of those jokes. It's not the like rolling on the floor joke. It's like,
Yeah.
okay.
Look at all these grades, dude.
Don't go like, oh wow, what's the joke?
Okay, that's a digression I will not go down because we don't have time. But anyway, all right. What I would like to say for this week. So today in the tutorial we're just focusing on integration, double integrals and a little bit on triple integrals. So please focus on that. I am starting to talk about vector fields today, just so that you've got it in your heads. And we will finish up vector fields in the lecture on Thursday. And then the lecture on Monday next week will be our last lecture. We will put it all together into the equations that we need for Maxwell's equations. Okay, so what is happening? All right, so just to recap where we've come from, and we've come from quite far away. We started out, we talked about vector-valued functions. So it was this crazy idea, you put in a scalar, like a time, and you get out a vector. Okay, and that was the whole parameterization thing. And we talked about differentiation of those things, and blah, blah, blah. And then in chapter 13, although we might have not quite have expressed it this way, we talked about scalar-valued functions of several variables, which is really where you put in a vector and you get out a number. Okay, so we talked about those. So if you looked at the two of those and you thought about mathematicians, you would realize that obviously you have to combine the two, and you want to look at things where you put in a vector and you get out a vector. And in a sense, you've already kind of seen things that sort of do that. Whenever you differentiate something like a displacement, you are doing something to the displacement. You take a function of it, you're differentiating it, and you get out a velocity. So it's nothing particularly hinky or weird that we're doing here. You've seen them already, we just haven't really talked about them explicitly. So why might we want to do this crazy thing, other than that it's kind of intellectually satisfying? Well, this might look familiar, it might not, but suppose that you want to talk about the force at a particular point due to gravity. Well, then you're going to be putting in a vector, a position vector, and you want to talk about a force, so a force is a vector. So we need to have some way of mediating between different vectors through functions. So here we have, for example, the gravitational force due to a point mass m located at P0. So this says, okay, I've got some little point mass that's just sitting here doing its little gravity thing, and what that equation says is if you give me a position anywhere around here, I can tell you the force that you're experiencing due to this little jobby over here. Useful. Okay, so you can see why this is going to come up a lot in physics, because obviously this is gravity, but in, for example, you can think about a charged particle sitting there, and then what is the electromagnetic force, things like that. So hopefully you can see why we would need this for all the physics that we're going to do. Okay, so we have a specific name for a function whose domain and range, so something that takes in vectors and spits out vectors, we call them vector fields. I've tried to find out why. I don't know. And the internet, well, the internet had some ideas, but I think it was lying. Okay. I will give you the most common explanation at the point at which it's most useful. Okay. So when someone talks about a vector field, what they are talking about is really a function where you put in a vector, you get out a vector. Okay. For those of you who go on and do more pure maths, this is not the same as an algebraic field. If that didn't mean anything to you, that's fine. If it does mean something to you, take heed. It's not the same. Okay. What do these things look like? Well, they look like you might expect. All right. So here is my vector function. So typically we use capital Fs and boldface, or I will use the little arrow over it
so that you can tell. So it's kind of the big F is to say this is a function, as opposed to, because the problem is that we're often talking about like a vector R like that. That's just a vector, and we want to differentiate it. And if we just wrote that, we wouldn't know if that's a vector or a function. So we're using a big F to say, or a big H or big G to say this is a function. Here's the vector that we're putting in, and the vector that we get out is written like this. And hopefully you're looking at this and going, wait, what? So this is where I get so frustrated with mathematicians, because it's like they try to be consistent in notation, but it's just not. So we have previously been using 1, 2, and 3 to indicate derivatives. Here these are not derivatives. These just indicate that there is some scalar function of x, y, and z which you put in, which will give you the x component. There is some scalar function f2 which you put x, y, and z in, will give you the y component, and the same for f3. Okay, so that's just a heads up. These are not derivatives. Sorry. Okay.
Sorry, I was a bit confused. Does that mean that when you put in the vector in your big F function, you take the x value and that will be your first your value for I?
So let me give you an example. Let's just write an example. All right, give me your favorite function of x and y.
A circle, x plus y squared. X squared plus y squared.
Okay, what's your favorite function of x, y, and z?
That's a good question. I don't know if I have one yet.
X plus y plus z.
Oh, that's pretty basic one. I'm taking that.
X, Y, and Z?
It's up to you.
3x.
Okay, so the point is that what we've got, if we look at this thing over here, we would call this f1, we call this f2, and we call this f3. And they're scalar functions because you put in your x, your y, and possibly your z into here, and you get out a number. And that number, or you get a for a particular x, y, and z, you get a single number, which is the component there.
That's your expression of f, and that's how you're always going to write it out?
It's probably how I would, yeah.
And that's given to us. The I component is this expression.
Yes.
Because we need an extra order of 3 variables for you to group them within.
I mean, this is, so f is a vector. So you might write it like this. You could also use your vector notation. Whatever vector notation floats your boat. Yeah.
So kind of like a gradient generalization would be like a matrix with partial gradients? Or?
Yes.
Okay.
Kind of, yeah.
So what would you do if you then derive it a second time? Would you then get like a... You won't
I think
get
my
a
head might
matrix
explode.
anymore, right?
My head might explode.
But you wouldn't get a matrix anymore, right?
You would probably get a tensor. It gets,
okay.
yeah. I think, well, anyway. Okay.
Yeah.
Okay. All right. A couple of other points of things you need to know. So if our z component is 0 and we don't have any z's in our x and y, then this is called a plane vector field. Basically, what you're talking about is a vector field that's living on the plane. So it's not a 3-dimensional function that you're thinking about. It's something that's living in a plane. Okay. Another thing that you'll often see, because we've seen that we will often just express position using an r instead of x, y, and z, in which case you'll write f of r, where r is your vector x, y, z. And if you were in different coordinates, you would have f of r, where r is, say, r theta phi, something like that. Okay. And just to kind of have, I guess, symmetry of notation, if you have a scalar valued function of a vector variable, which we've seen before, we will call that a scalar field. Okay, so we've a function of several real variables, so when we have one of these bunnies, put in a vector, get out a number, that's a scalar field. Put in a vector, get out a vector, that's a vector field. Okay. Okay, so why do we love these things? Because they are everywhere and they are basically what we need in order to talk about physics. You can't really do physics in any kind of meaningful way without vector fields. So for example, gravitational field, we've already seen, going to be a vector field. Electrostatic force, okay, so anything to do with GR, anything to do with special relativity, anything to do with Newtonian and classical mechanics, you're going to need vector fields. Anything to do with electromagnetism, you're going to need them vector fields. If you're doing any kind of fluid mechanics, you're going to need vector fields. We'll come back to this in a moment. If you're trying to model things like temperature in an environment or pressure, yeah, so basically it's all vector fields. Alright, now the thing to notice, remember when you took our gradient, what did you end up with when you took a gradient? What is the gradient? What nature of thing? Is it a zebra? Is it a scalar? Is it a vector?
It's a vector.
It's a vector. Okay, so even if you have a scalar field, which we've seen lots of, so that's where you put in a vector, you get out a number. If you take the gradient, you end up with a vector field. So this is going to turn out to be quite important. The gradient of any scalar field gives us a vector field. Alright, so this brings me back to why we might call it a vector field. So how do we visualize these things? Now, if you think about it, things were getting pretty tricksy with visualizing in 3 dimensions. When we were thinking about what happens if you put in a vector and you get out a scalar, that got complicated. Now we're putting in a vector and we're getting out a vector. How do you even draw that thing? And the answer is, well, not very well. But you do what we always do, which is this, when we were trying to draw things that were 3-dimensional, we drew level curves. So we try to simplify down and try and get a feel. So if we look at our gravitational field of a point mass, we can plot some vectors in a plane section of the field to visualize the vector field. So this vector field lives in 3D space. But let's just look on the xy plane and see what some of those vectors look like. Okay, so I'm imagining I've got my xy plane and I'm just going to put my little point mass at the origin, just to make life easy. What do I want to do? Okay. And now I'm just going to draw some different vectors. So if I imagine that I'm starting over here, let's say at 1, 1. So if I put in the point 1, 1, what will I get out? Well, I'll get, so let's let, well, then I'm going to get, and I've turned this is 0, 0, 0, so that's making life easier. So I'm really getting
this. So I'm going to, so firstly, what direction is this pointing in? So let me try and make this clearer.
Towards the origin?
So there's a negative, and it's, so the one direction is like this, but there's a negative, so it's pointing back in this direction. So it's a vector of some magnitude pointing there. Okay. And in fact, if you draw some more points, you'll see that they all point back towards the origin. And if you think about what this is trying to express, it's trying to express the gravitational pull of a point mass. Well, it says if you sit over here, you experience a pull towards there. And if you look at, we're dividing by r cubed, so the further away you get, the bigger you're dividing by, so these will get smaller. So you end up having, so if I was out here, I'd have smaller little vectors. And the further out you get, you'd have even tinier ones. And again, it's expressing what we know from gravity. The further away you are, you know that gravity drops off as 1 over r squared. Okay, so it's just kind of expressing, and you can imagine now, if we take this and imagine it in our 3D space, you'd have all these little vectors kind of in concentric spheres, getting smaller the further away you got. Okay. Why field? The one idea is that basically when you plot all of these in a plane like this, it kind of looks like a field of things growing. Okay. All right. I think we will call it there. I think you're all looking at the phone date. Are there questions? Okay, so just so that you know, so Thursday, if you came in late, there will be a lecture for an hour, and we'll be finishing up basically talking about vector fields. So we have to do all the things with vector fields that we've done with all the other functions. We need to be able to differentiate vector fields, we need to be able to integrate vector fields. Thursday there's a lecture from 2 until 3, and then prep from 3 until 4.
So we'll have half an hour extra. Right?
We have an hour lecture from 2 until 3.
Yeah, but usually we have 1.5 hour tutorial.